Hello everyone. In this activity we're looking at a data set with two separate independent variables and one dependent variable, and we're going to do a two-way ANOVA in jamovi. So in order to do this, we're going to start by labeling our variables. Right now we have our two independent variables are the expertise level of the people playing a game and also piece configuration. So this example is that we're looking at a two-factor design where we have expert and novice chess players. And they are looking at two different chess boards. One where the pieces are in a game configuration that makes sense as if people had been playing the game, or they're in a random configuration. Both groups see these piece configurations very quickly, and then they are asked to recall how many of those pieces they can locate correctly on a chessboard. And so our dependent variable here is the number of pieces they can correctly locate. So I'm going to change these labels. I have expertise levels of 1 and 2, where 1 is novice and 2 is expert. So I'm going to change the labels here so that 1 is novice and 2 is expert. And then after I do that, I'm going to go ahead and close up that menu. And then my piece configuration, I have 1 is a game configuration and 2 is a random configuration. And then after I've done that, I will close that menu. So to run the ANOVA, I click on the ANOVA menu and then select Analysis of Variance, or the ANOVA. And then, once I have this, I'm going to move slowly. I guess it's stuck here. There we go. So we're going to look at the dependent variable is pieces located correctly in that box. And then I'm going to move my two independent variables into the fixed factor box. I have expertise level and piece configuration. Now, that'll automatically give you the ANOVA summary table, but it won't include effect sizes. So I'm going to ask for omega squared and partial eta squared to get those for each effect. So we're looking at three effects. We're looking at the main effect of expertise level, the main effect of piece configuration, and the expertise level by piece configuration interaction. We're going to start by looking at the interaction. And you can tell here with our interaction we have a p of 0.00006, a very small p-value suggesting that the difference or the interaction that we're observing is unlikely to be due to sampling error. But all that means is now we know that, well, expertise level and piece configuration interact to have a unique effect on people's recall of the pieces located. But we're going to need to look at simple effects to interrogate this and understand it more fully. All right, so we're going to look at the simple effects here under the post hoc test menu. Right. Before we run the post hoc test, though, let's take a quick look at the estimated marginal means. So we can look at the means for the cell means by moving piece configuration and expertise level into the same box. That'll look at two variables simultaneously. So we can see here that for novices, it looks like overall their recall is not great. They were able to identify about 9-ish pieces and where they were supposed to go. Experts here did really quite well within the game configuration, right? They recalled about 14 pieces in their correct location, but when it was random, they did not do very well, right? They also only recalled about 9 pieces. So what we need to look at is these simple effects. So we're going to look at the simple effect for novices, and that is comparing these two means. And we're also then going to look at the simple effect for experts, comparing these two means. To do that, we're going to click on post hoc tests and move the interaction term over into the box. And then click on no correction, unclick Tukey, and then ask for Cohen's d in the confidence intervals. So we're looking at 4 novices comparing the game and the random configuration here. So this is novices comparing the game and the random configuration. We are comparing them and get a p-value of 0.37, which tells us that this difference we're observing between these two means is probably just due to sampling error. Now when we look at experts, this is at the bottom row, experts in the game, expert for random, we get a mean difference of 4.8 with a p that's less than 0.00001. Right? This difference here is unlikely to be due to sampling error. Right? This difference seems to be a real difference in that experts were better with the game configuration than the random configuration. So novices, it did not matter, according to our simple effects, in terms of whether or not they saw game or random. They didn't do great. But experts, their performance was much better when they saw a game configuration of pieces than a random configuration. Right? So the effect of game versus novice configuration depended on whether or not you were a novice or an expert there. Okay, so that is our interaction. Next, we need to look at our main effects. So we have a main effect of expertise level and a main effect of piece configuration. For the main effect of expertise level, our p-value is 0.00035. So I'm going to get the marginal means for expertise level by adding a term and looking at expertise level in term 2 and drag it over there. And I'm going to look at the marginal means. Oh, and I can look at a plot. You can also look at a table by clicking on the tables box here. Okay. So here, if we look at experts versus novices, on average, experts appear to have done better than novices. Experts got on average 11.63, novices got on average 9.13. Okay. And our p-value there of 0.00035 tells us that that difference is unlikely to be due to sampling error. Now, that doesn't tell the full story. These main effects can be really misleading, so you have to be very careful interpreting them. Yes, experts on average did better than novices, but that's totally driven by this particular data point. Experts did much better with game configuration than random. Experts were no better than novices in that random condition there. Okay, then we have a main effect finally to look at of piece configuration. We have a p of 0.00448, which tells us that that difference is unlikely to be due to sampling error. And now I'm going to go over to my estimated marginal means and add a term and look at piece configuration. And I have game and random piece configuration. Overall, performance was higher with game configuration than random, okay, on average, right? But we're ignoring expertise here. So this was true, right? On average, game configuration did lead to higher performance than random configuration, but remember that interaction, right? It's not true for novices, right? The whole point of this, it was this expert condition where they did better with the game than the random. Okay, the last bits of information you often need to report a two-factor ANOVA is getting standard deviations for each of your means. Jamovi gives us standard errors. You can convert them into standard deviations yourself by multiplying by the square root of n. Or you can go to the exploration menu, click on descriptives. And then I'm going to move pieces located, my dependent variable, into the variables box. And then I can split by one variable. Right? And if I split by this first variable, expertise level, I get the mean and standard deviations for the marginal means. I can do the same thing for piece configuration. I get the means and standard deviations for the marginal means for piece configuration. And you can also look at them both at the same time for the interaction to get the numbers inside the table, where you get the means and standard deviations for each cell in the design. Okay, so that should be all of the information you need to run a two-factor independent measures ANOVA in Jamovi. And good luck with your ANOVAs.